So previously we have seen the relation of work done by spring force and how the kinetic energy is changing. So the relation that how the potential energy is changing. Sorry. So the relation that potential energy change is equal to negative of work done by spring force is being proven valid at every stages. Now we will see how does the kinetic energy behave in this case. So firstly, there is a common spring of natural length L. Now what has been done, that this has been pulled somewhat to this position and has been left. Now if you try to pull it up to this position without giving it any kind of energy, any kind of kinetic energy, we already know that you have already given it, this is the first position, this is the second position. So you have already given it potential energy half K x1 square if this is the length x1. So if you just leave it at that point, then what will you call the total mechanical energy to be? E2. If you just leave it at that point, then what is the velocity at that point? It's just 0. So velocity is 0, it means kinetic energy is 0. So energy is just half K x1 square. Now if it is just been left, then it means at any point of time this spring force is acting on it, trying to pull it to this position. The spring force will drag it to this position as soon as it is in left. Under the action of a spring force, it will move from this position. Now basic kinematics says that if any object is under action of a force, it will be accelerated. So it will gain some velocity. It means by the point this object comes here, it has gained some velocity. It means this time kinetic energy at position 3 is definitely not going to be 0. The question is what it would be. Before that, if we find out the potential energy, it will be much easier for us because this is at the natural length. No, x is 0, so it will be just 0. Now, there are two ways basically, or actually three, to calculate the kinetic energy at this point. We will start from the very easier one, or we can go another way out there. If you want it to be a tedious one, then what should be? First of all, I must make it very clear that this case of motion from this point to this point cannot be solved using Newton's equations, because Newton's equations are applicable only when your external forces are constant. And in this case, the forces are not constant, it is depending on x. So we use this relation V dV equals to A dx. This is a universal relation. This has been derived especially for the case of non-linear acceleration, and then we just integrate it. So initial velocity is 0 at this point, so it will just v square by 2. And what is a? A is not constant, so it cannot be taken out of this integration sign. Or right now I can do this calculation here. So it will be v square by 2. Integration of a. A is your kx by m at any point of time. Suppose at this position, from this element x. So somewhere here, this is the initial point of the path, this is the final point, this point is somewhere here. So the force A acceleration is always towards this direction, towards this normal position. So kx by m into dx. So that will give us k by m x square by 2. So we found that velocity will be root under k by m x. If m is the mass of the object. So if we take out the kinetic energy at this point, it will be what? Half mv square. So half mv square means k by m x square. Now cancel, we get half kx square. What was the initial x? Limit was x1, it will just x1. So how nice it is, because what is this? This is nothing but our initial energy. So the magnitude wise our total kinetic energy here is just half kx1 square. And you feel 0, so total energy at third position is also half kx1 square. So this much of calculation which we did could have been avoided had we have been keeping in mind the basic law of conservation of energy. What I said, that if only conservative force, here the only force acting is the conservative force, the spring force. So if only conservative force is acting, no external force, no friction, no any other force, then your total energy is going to be conserved. Now please make a note. When we started this point, the total energy was also 0 and E1 was 0. There was no energy. But from this point to this point, we applied some force. That's why it could be dragged. So that's why we are not considering first case, first part. We have started our mathematics from second part. Why? Because in the first part there was some external force. So that external force gave an energy equivalent to half kx1 square, and then it vanished. We just left the block. So then it vanished. So it left the energy half kx1 square. So after that point, after this position 2, there are no any external force. So after this position 2, the net energy will be conserved. So what do you think? That will the block will stop here or move forward? Basically, because of inertia, it will oppose this string. Because of inertia, it will further move away. Now, when it further moves inside, there will be a retarding force start acting to pull it back, and that will be also what? Kx. So slowly its velocity will decrease, kx will increase. At a point, it will come when it will stop. Now we have to calculate what this point is. Now this time we are going to be smart. We are not going in any kind of mathematics. We will just use our concept. The concept is that at this position, fourth position, it's going to stop. It means kinetic energy 4 going to be 0. It means the total energy which has in form of kinetic energy will be converted to the form of potential energy, and that expression is half k x square. So to be equal with third case, it should be 1. It means it will further go inside x1, and your energy 4 will again be half k x1 square. The total energy is conserved. Kinetic energy is oscillating from 0 to maximum, then 0. Potential energy again maximum, 0, ratio. So when it is at the very extreme ends, the potential energies are there. When it is at the midway, the kinetic energy is there. Basically, your energy is oscillating between kinetic energy and potential energy under the action of only conservative force of spring force. Had there been friction, had there been any external force acting, then these things will not be valid. Then we have to apply from very basics. What the basic is? Let's suppose there is any external force. So in that case, change in mechanical energy EF minus EI will be equal to work done by that external force. We will not consider the work done by conservative force, because that work done is basically just changing your potential to kinetic, kinetic to potential. So that external force will bring into changing your mechanical energy. So if this force is positive, your EF will increase. If this force is negative, your EF will decrease. So EF greater than EI when work external is greater than 0. EF less than EI when work external is less than 0. This may include your non-conservative force as well. This is your friction force. So especially in the case of friction force, we find negative work, because displacement and force always opposite to each other. So that will be negative work. So negative work means its final energy will reduce. So it means that if there is friction and then you leave this, by the time it reaches here, the kinetic energy will have been reduced. By the time it reaches here, will it reach here? No, it will not reach here. So under the action of a spring force, this will not be x1. So this is somewhat x2, and that will be less than x1 when F is there, friction is there. So concept, all the basic concept we have understood, that if we apply any external work because of any non-conservative or any kind of external force, that will change your total mechanical energy. It will either increase it up or decrease it down. If it's positive, increase. If it's negative, decrease. So friction is an example of negative work done. So that's why it will always decrease. So your final position will not be x1, rather it will be x2, where x2 will be less than x1. Because we have already seen that if x2 is less than x1, your potential energy final will be less than potential energy. And so we get the case of damping, where slowly this will actually get back to its natural position. Otherwise, in ideal case, if you just pull a pulley, leave it, pull a spring, just leave it, then infinitely it will move on oscillating. But in real life, you see that it doesn't happen. You take a spring, pull the block, and just leave it. It will oscillate definitely, but slowly its amplitude. This distance we call it as amplitude A. So slowly its amplitude will decrease down every step by step, and finally it will just get back to its natural position where energy is in zero. So these were the basic concepts of work energy and power. Power is nothing we have already explained. Power is just capacity to do work, how quickly you are doing work, energy, work for time. So those things will be much more elaborated and much more clear when we will deal with problems. And subsequent lecture we will start solving problems. Thank you.